Now, we are going to explore the motion described by the Larmor equation. And for understanding the motion of magnetization, it is important to introduce a concept on how to simplify the description of the motion, how to make it more accessible, understanding what exactly happens. And this simplification is based on using a rotating reference frame. And why do we want to do this? Well, first I want to go and explain what is a rotating reference frame. Well, a rotating reference frame is a frame that rotates about the z-axis in the laboratory frame. So that's our reference frame. We'll rotate around the z-axis. We'll assume the magnetic field is vertical in this case. So why would we use a rotating reference frame? Well, we've seen that the equation of motion, the Larmor equation, gives us a rotation around the magnetic field. So if we have a magnetization that's not parallel to the magnetic field, then it will rotate around that magnetic field, just like the wheel the bicycle wheel that we have seen rotating. So this is similar to a carousel. So we are on a carousel, and if we look at a carousel, the motion on a carousel, the motion of people on a carousel from the outside, it's fairly complicated because we have any motion on the carousel superimposed by the motion of the carousel itself. That's what we see from the outside. And if we are now put ourselves on the reference frame on the carousel, anything that happens on the carousel with respect to the carousel is stationary. What we do in classical physics, I'll do the analogy here, is that we are sitting, let's say we are sitting on a chair without motion. Then we have a force, that's the centripetal force towards the center. That's the force of the chair that pushes us and maintains the circular motion that we have. But we feel from our inertia that there is a force that pushes out against the chair. This is not a physical force, it's purely the inertia that our visual system senses. It is a fictitious force. So we have, similarly to the motion on the carousel, we have the magnetization vector. Here turns here in the lab frame. And if we're in the rotating frame, the magnetization vector is stationary. So we can, just like in the carousel, if we have our magnetization that is precessing around the magnetic field B0, we can put ourselves into a reference frame that rotates with the magnetization, and there the magnetization becomes stationary, just like the person here on the carousel. So what are the consequences of using a rotating reference frame? I'll start here with making the analogy to classical physics. In this video you see kids throwing a ball at each other. First seen with the camera from above, the ball goes pretty much in a straight line. And then when the camera is put on the merry-go-round, you see that the ball goes in a very curved motion, and which seems odd. I will show in the following with an animation this effect. And basically the situation we're considering here is that we have a pendulum that swings with a amplitude equal to the disk radius and a period that's equal to that of the disk that rotates below. So here's the disk, the triangle indicates the motion of the disk. Now we have the pendulum swinging. Its period is exactly to the period of the disk. That's the equivalent of the merry-go-round. So we're throwing the pendulum straight line. This is the bird's eye view. It's in the inertial reference frame. Everything is the way we normally see it. Now what we're going to do is we're going to put ourselves into the rotating reference frame of the carousel. And to help your eye see the motion, I have indicated here the coordinate system by the spokes on the carousel. We'll take away the motion seen from the outside, and now train your eye. Do you see what motion you see with respect to a carousel? Here it is. So it is indeed a circular motion. Our object, seen from the carousel, undergoes circular motion. And just to convince you that I'm not cheating here in any way, I'll put back the horizontal line. So this, seen from the outside, we still see the motion of the object of the pendulum swinging back and forth in a straight line. But from the carousel, seen from the carousel, from the merry-go-round, we see it as circular motion. So that's essentially the motion that is seen if our reference frame that describes our motion is equal to that of the merry-go-round, the carousel, or the rotating reference frame. Now what we have done here is we have just changed the mathematical framework on describing the motion. We go from straight motion to circular motion depending on whether we describe the motion in a reference frame that rotates. That's a purely mathematical description of the motion. And we still want to have a proper description of the motion, and to do that we want to look at the motion in our merry-go-round. We want to add all the forces that act on our ball or on our object. In the end, we still want to have a proper calculation of the acceleration. That's Newton's second law. So to get to the proper acceleration here, to describe this motion here, get the proper acceleration, we have to add two fictitious forces, centrifugal force and the Coriolis force. Now bear in mind, those two forces have nothing to do with physics as such. They are the consequence of the fact that we mathematically change our reference frame from a non-moving or from an inertial frame, that's typical non-moving reference frame, to one that rotates around the axis Z. These forces have to be added so that we can describe in the reference frame that rotates, this one here, that we can still arrive at calculating the proper accelerations with Newton's second law. Now, you might ask, why am I transgressing into classical physics? What is the link to magnetic resonance? Actually, the link is there. We have a description, a mathematical description in a reference frame that rotates. In classical physics, we need to subtract or add two fictitious forces. And as you will see in the next slide, we have to do a similar thing for the proper description of the magnetization in the rotating reference frame, except that we are not going to deal with forces. We are rotating in the rotating reference frame, not in a physical reference frame. It's a reference frame linked to the magnetization. So how does the equation of motion for the magnetization change if we change the reference frame? So we'll now say we're going to put ourselves into a reference frame that rotates with omega RF. That's in radians per second. And in that reference frame, we observe the magnetization rotating with a Larmor frequency, big omega here, which is given by the Larmor frequency, gamma B0, minus this omega RF. That's the angular velocity of the rotating reference frame. We can now associate to this omega, this observed Larmor frequency. When we can observe, we can relate this to a magnetic field, and we'll call this magnetic field delta B. So big omega is equals to gamma delta B. Or if we now stick this in here, we can, and we use omega L equals gamma B0. The delta B is given by B0, the external magnetic field, minus omega of the rotating frame divided by gamma. So, in the lab frame, where our rotating frame does not rotate, that's the lab frame, omega RF is 0, and the Larmor frequency that we observe in that reference frame is equals to omega L, and delta B is equals to B0. So now what we want is, in our rotating reference frame, independent of the frequency with which I take my reference frame to rotate at, I want the Larmor equation to be true. For it to be true, I have to increasingly subtract a fictitious magnetic field. And this magnetic field is this term here, omega RF over gamma, that we have to subtract from B0. So this is not unlike the classical mechanics, where we take our physical forces. Once we're in the rotating reference frame, we have to add or subtract, depends on how you look at it, the centrifugal force and the Coriolis force. Here, in order for the equation of motion to work, we have to subtract a fictitious magnetic field. That's a consequence of the motion, to make the equation of motion work. We still want this equation to be true in any of our reference frames. So how does this work? So we'll look at first at the lab frame. We are far away from the Larmor frequency. So this is our rotating reference frame. Let's say it is at 0. Here's our Larmor frequency. On the horizontal axis is frequency. Then this difference in frequency is given by omega here. And if we look in this reference frame at the motion, we have a delta B, which is given by this term here. So if we say omega RF, the reference frame frequency is 0, then the delta B is equals to B0. Now, what is the motion of magnetization that we observe? Here's the magnetization. We'll say it is in the transverse plane, so XY. And if this magnetization is a transverse plane, then it will precess at a very high frequency dictated by gamma delta B around the magnetic field B0. This is what we term this off resonance. We're far away with our rotating frame from the Larmor frequency. Now let's get a little bit closer, and we'll go closer with our rotating frame frequency. And now the motion is slower. We're starting to approximate the Larmor frequency. This is as if we have first started out observing a carousel, it turns, and now we're starting with our reference frame starting to move in the direction of the rotation of the carousel. Then the carousel from that reference frame will turn at a slower frequency, and this is what we see here with the magnetization. As we have increased our omega RF, we have increased this term, we have to subtract this fictitious field as a consequence of the rotating reference frame, the omega RF divided by gamma. So our delta B is now reduced. If you go even closer, then if we're now relatively close to the Larmor frequency, the magnetization will noticeably the precession will be noticeably slowed down, and we have to subtract omega RF as it's increased a bigger fictitious field omega RF over gamma, and the delta B is now decreased because this motion here dictates the frequency of precession here. And now if we go essentially to the Larmor frequency, then our big omega goes to 0 and our magnetization no longer turns. I'm still showing a turning magnetization here, otherwise it's a very boring animation. But essentially, if our omega RF is equals to the Larmor frequency, then our magnetization, we are rotating exactly at the frequency with which the magnetization rotates around B0. And in that reference frame, the magnetization is stationary, so it does not move. If the magnetization does not move, then it is stationary in that reference frame. So the derivative of the magnetization with time is 0, so omega has to be 0, and that means that omega RF is equals to omega L, delta B is equals 0, and this case we call on resonance, where omega RF is equals to the Larmor frequency. That's the on resonance situation. That's the situation as if you are on the carousel, and now your reference frame is moving exactly with the motion of the carousel. And so I want to show this precession of the magnetization, the Larmor equation, with a simulated experiment of precession. It's a macroscopic experiment. It simulates how spin precession works. We'll just take the view of the lab frame in this experiment that follows. So this is an experiment which simulates the motion, the motion of precession, the Larmor equation on a macroscopic scale. We have in this yellow ball, we have a magnet, and that magnet will align itself based on the magnetic field. However, it is required that it has, just like the nuclear spin, that it has an angular momentum. So if I don't have an angular momentum here, this ball is, and I turn on the magnetic field, the ball will just go down, as we have seen with the wheel experiment, the suspended bicycle wheel. So now what I will try to do is I will try to give this ball a spin. I'll set it into circular motion. Nothing happens now. Now I turn on the magnetic field, and you can see it is turning around in one way. And if I stop the magnetic field, it stops. It just turns around its axis. And if I invert the polarity of the magnetic field, it turns the other direction. And those are the properties of the Larmor equation demonstrated here with this macroscopic experiment. We have today in the course talked about that the equilibrium thermodynamic magnetization is along Z. And we want to look at how we can get the magnetization to change its orientation. And this I want to do for the end of the lecture. We'll resume this description, but it's an example of describing the motion in the rotating reference frame. I want to illustrate how the magnetization can be manipulated. So if we're putting ourselves into a magnet, we will develop a thermodynamic equilibrium magnetization M0. If we take the reference frame that rotates with a Larmor frequency, that's the on-resonance case as we have described it. Then we have to, in that reference frame, we have no net magnetic field, so the magnetization is stationary. We have no B0, the omega RF over gamma just cancels the B0 term. Now in this reference frame, we will apply an additional constant magnetic field with magnitude B1. We'll give it the name B1, and it shall be somewhere in the transverse plane, along X or Y. Doesn't matter whether it's along X or Y for the purpose of this discussion, and we'll apply this additional magnetic field B1 for a time tau. So question, what motion can we observe for the magnetization in our rotating reference frame? Well, let's look at the equation of motion. We have said it is always the same. The derivative of the magnetization is equal to minus gamma, the magnetic field, times the magnetization, and the times here is the vector product. Now, since we are rotating in the reference frame that rotates with a Larmor frequency, the B0 term does not exist in the equation, and we've said the B1 here is constant. It is in the transverse plane, so it's perpendicular to B0. So what motion can we observe for the magnetization if we start out with equilibrium magnetization? Well, the motion is the same, and in this reference frame the magnetic field is constant, so the motion that we observe, this is what we've discussed. This equation says that the magnetization, equilibrium magnetization, will now start to precess about B1. So it will rotate about the vector B1 at a constant angular velocity. So this angular velocity in radians per second, gamma V1, has the frequency of gamma B1 over 2 pi, and it has the period of 2 pi over gamma B1. Of course, this is the relationship between frequency and period. So let's visualize this. We're in the rotating reference frame. We have our coordinate system in the rotating reference frame. We have this constant B1 in this rotating reference frame. We have the equilibrium magnetization M0, and now we have applied this B1 for a period of tau. After this time tau, the M0, the magnetization, has precessed about B1 by an angle alpha. If the B1 is along X, then M0 will precess in the ZY plane, and after time tau, it has undergone a rotation by the angle of alpha. This angle is important, so I'll define it here. This angle is called the flip angle. It describes the angle of rotation induced by the, in this case, by this B1 field that was applied for tau seconds. What are the special cases of the flip angle alpha? Special cases are 90 degrees. If alpha is 90 degrees, we call that excitation or full excitation. That is all the magnetization that's along Z. Here in this example, its equilibrium magnetization is rotated into the transverse plane. So we rotate M0 from being along Z into magnetization in the transverse plane, and we often call this MXY for the transverse magnetization. So that's this case here. We have rotated the magnetization into the transverse plane. If we now double the duration so that we get an angle of 180 degrees, then that is called an inversion. We go from an equilibrium magnetization that's along Z like this to an magnetization that's opposite, minus MZ in the minus Z direction, and that is called an inversion. So that's the situation here after 180 degrees. And if we leave the B1 on, then the magnetization will persist around B1 for as long as we leave this B1 field on. Now B1 is called the radio frequency field. Why? Can you picture this? Why is this called a radio frequency field? Well, it helps here to remind ourselves, we've said B1 is stationary, that does not change with time in the rotating reference frame that rotates with the Larmor frequency. What does that mean if I look at it from the outside? What form does the B1 have? Well, my hand's already telling you it's rotating. So in the lab frame, seen from the outside, we have actually the B1 is a time-dependent field. It is given by B1, the amplitude, and it rotates exactly with the Larmor frequency, omega L. Now, why do we call this radio frequency? Because if we look at the Larmor frequency, we take for protons the gyromagnetic ratio, which is 42 megahertz per Tesla. We calculate the Larmor frequency in hertz, and we'll find this is typically on the order of 100 megahertz. So it's perfectly in the range of radio frequency. Actually, here it is in the range of truly the radio frequency 100 megahertz. And that's why the B1 is called radio frequency field.